us off and also turn our microphones off so that we don't have any interruptions. Are you ready to upload your presentation? Can you share your screen?
Sure. Just a moment, please. Okay, so do you see my screen?
Yes, we see your screen. You might want to put it into presentation mode.
Which doesn't work. I mean, you don't see it in the presentation mode. So
because it jumps onto a different screen. That's fine. You can do it.
I just go on like this. Yeah. Okay. So good morning, American friends. Good afternoon, European friends, and good evening, Asian friends. Now, this is my seminar on, well, for this occasion of Design Society seminar series. And when Claudia approached me, I wasn't sure what I should talk, but yes, I looked at other people's presentations, and I was also present at Chris McMahon's presentation, and then Daniel's presentation. So I'm just following the kind of format all other people are using. So the format is I'm going to review what I have done in the past for design research, and a little bit different thing is I would like to analyze some of the research pieces I have done, and I would like to categorize, I would like to evaluate, criticize myself if they are really good research or not. And by doing so, I would like to draw some advices for younger people who like to establish design research career. I don't know if it is a good idea or not, but or this is my some cents or pennies for the design society. So first, this is my background. I'm now currently, well, Vice President, Dean, and Professor at the International Professional University of Technology in Tokyo, which is a very new university. And this university just opened in April. It is meant to be a totally different formula as a university. It is teaching students with a lot of hands-on experiences. More than half of the staff members are coming from industry. We are focusing on information ICT technologies and computer-based entertainment technologies. So basically it is a software-oriented university, and we have 200 students this year. I don't know if it is going to be a success or not, but this is a little bit a kind of experiment for everyone in the university. And before that, I was in Cranfield, and before that, I was in Delft, and before that, I was in Tokyo. One advice to younger people: don't do this. The reason for this is that you end up with a very bad pension whatever it is. So don't mess up your pension savings. So don't do this. But anyway. So this is the overview of my research activities at the University of Tokyo between the beginning of 80s until 2002. I looked at design theory and design process modeling. I started the research activities on intelligent CAD systems, and we tried to use AI technique called qualitative physics, and we tried to build up knowledge base of ontological design knowledge. I believe we are one of the first groups which started to use the word ontology in design. We developed a function modeling system called FBS, function behavior, not structure, but state modeling. So these are all design support side. And then we looked at the development of specific machines. One of them was self-maintenance machines. Self-maintenance photocopier was commercialized. We also developed so-called cellular machines. And then at some point we gave up. And then a company called Amazon developed similar robotic system. So after all, it wasn't a very bad idea. It was actually a very good idea. I also started research in the area of sustainability. So we worked on post-mass production paradigm. From that, we started so-called life cycle simulation. And finally, we began the concept of service engineering. And then I moved to TU Delft in the Netherlands. What I was very much interested in at that time was architecture building, architecture of the complex systems, not the buildings, constructions, but architecture of multidisciplinary complex systems such as photocopiers, such as MRI systems, such as a very large-scale warehouse or a baggage handling system. We were also interested in model-based engineering. We developed, together with my colleagues, we developed a design method, creative design method. We also looked at human assisting robotics. Then I moved to Cranfield. We were pretty much obsessed by the idea of automated maintenance. So I ended up with cleaning robots. I also looked at the concept of resiliency in machine behaviors. So I was wondering how we can build resilient behaviors of machines. So that's what I was doing. And that was about the end of the whole journey, so to speak. And here we are now. Now, I would like to tell you about some of the journeys I have made. And one of them is intelligent CAD. When I was a PhD student, I was very much fascinated with AI. At that time, it was pretty much knowledge-based engineering, knowledge engineering kind of ideas. And we tried to implement a rule-based system for automated design. And I myself coined the term intelligent CAD. At one point, it was busted by Ken McCallum. He wrote a paper titled, "Does Intelligent CAD Exist?" Well, he was very negative, and he only said, basically what he said was, intelligent CAD exists as a vision, not as a real system, so to speak. But anyway, we are working very hard to develop intelligent CAD systems. And I'm not saying that we succeeded. We soon realized the limit of what we can do due to the sheer size of the workload, sheer size of what we need to deal with as design knowledge. So we had to change the direction, and we instead of developing automated design system, we tried to develop a framework design support system, but equipped with deeper model-based knowledge as opposed to shallow rule-based knowledge. And then we developed a special mechanism called Metamodel. And this Metamodel is model of models. Therefore, it must be able to integrate different types of models. We tried to do this based on a theory called qualitative physics process. A theory of Ken Forbes, QPS, and the system allows reasoning, qualitative reasoning, and it also allows plugging in existing models for specific purposes. So we developed a framework called Metamodel, and the system allows to take in different types of models. And to do so, we needed engineering to describing physics and engineering knowledge in the Metamodel. We did it in the so-called ontological way. So that was pretty much what we are doing in the 90s, and we realized that when you talk about design, you really have to find a way to represent functions. And in 1990, even before John Jarrow, we wrote a paper on function, behavior, structure. But then, because we are using QPS-based reasoning system, and we integrated this reasoning system within our function modeling system, we thought it was a better idea to call it function, behavior, state modeling. We changed it very quickly. And then, this was the origin of FBS for us. And the system was able to reason about the physical behavior of design objects, and not in the numerical way, but in the pretty much qualitative way. And I thought that was the way to go. Now, unfortunately, once again, we ended up with the problem of, or the, well, sheer size of the design knowledge, and that wasn't that successful, but still, I still believe that it was a good push, yeah. In parallel, we also looked at design process knowledge, presentation, and we tried to formalize design protocols, and this was a little bit successful in the sense that you can actually simulate design reasonings. We could show logical simulation of design processes. All of these were developed into a Smalltalk-based implementation called Knowledge Intensive Engineering Framework. And that was all what we are doing in the late 90s and the beginning of 2000. So this is what I dug up from my collections. This is the initial FBS model. Once you have described, don't ask me what it means, but it is, I guess it is a representation of electrical relay. Then it is able, the QPS-based behavioral reasoning system can generate all possible behaviors of this relay, and behavior will be traced as state transition. And then this is a different example. This is the function model of photocopier. And photocopier has well, a couple of components which can execute functions pretty much similar to each other. And that means when there's something wrong with the photocopier, you may use all these redundant functions to compensate the lost functionalities. And the system reasons out how you do it. And knowledge intensive engineering framework. So this is the output around 1999, and yeah, this is one of the components of cellular machines, and all of these models were integrated through Metamodel. Now, much later, we were also interested in developing complicated machinery like this one. And we used our Kiev or FBS modeling to explore different types of architecture for this type of photocopiers. And this was pretty much well, successful in a way that it could generate automatically different types of possible physical combinations of physical components. and that would mean different types of photocopier engines, printing engines, and the system could help you to identify what sort of timing you have to run this, well, run the system, and so on. So this is architecture one. This is cooling of fusing of ink on the paper, and you need to cool the print. And how do you do that? Well, you have to have a heater, you have to have a preheater to heat up the paper, and after printing you have to cool it down very quickly, otherwise well, the toner or ink will stick to the other anywhere else. So different types of print cooling mechanism you have to explore, and this is what the system generated. One type is this one, 130 first, 150 first is this. Okay, you can actually generate as many as you want. And then the system helps you to develop more quantitative model. So in this case, we used MATLAB to generate quantitative models, and the system was almost automatically able to generate and evaluate different types of architecture. That's what we have developed. Now, this is very coming from very old paper of 1990 about design process modeling. So the idea was to use abduction and deduction to simulate design processes logically. We developed design simulator, and the design simulator could logically trace back design protocols. And this is a different line of research. We were also interested in self-maintenance. As I described, we worked on qualitative physics. And we knew that qualitative physics at that time was pretty much used for diagnostic purposes. And so we developed first qualitative physics-based failure simulation, and we used this simulation to diagnose failures. And then, because there is a model of the system, you can actually generate recovery plans, which means failure recoveries. And so we developed a self-maintenance photocopier. The machine could maintain itself very well. Unfortunately, the company couldn't. So we ended up with a broken company. Yeah, that was the story. We were also interested in cellular machines. So one cell is of this size, it's pretty big, but it is composed of rotating table, and it can move around all these pallets. And on the pallets there are packets that you like to take out. there is an exit cell, and exit cell asks if somebody else has the wanted packet. So someone's if you want to take out a component, then you say, I need a component. If you like to have a product, then you just make a call for this product. For example, product A and B. And if there is no pallet, no cell which is carrying this product, then this information about product AB allows the cell to decompose it into multiple components to be assembled. So when you need product AB, it's a combination of product A and B. Then after some period of time, you don't get it. Well, if that's the case, then exit cell makes a different call for product A, component part A and part B. And these decomposed two calls will be issued from the manipulator cell. So the cell manipulator receives part A and part B separately, and the manipulator assembles part A and part B into a product AB. It can also decompose product AB into part A and part B. And by doing so, well, it is a remanufacturing, so you may have to clean the used product AB, or you may have to use different tools to decompose the product into parts. So it can carry also attachment tool to screw or unscrew or drill, and the manipulator knows how to decompose them. So this was the idea we developed, a cellular remanufacturing system. Then we thought it might be a good idea to make all these cells movable, moving cells. Now, this was all what we developed, and that was the end of our imagination. But then there's no connection between us and the company called Amazon, but they developed similar ideas. They came up with similar ideas, and now they are using these moving cells to store goods in their warehouse. Well, this is what they are doing nowadays. I was also interested in resiliency for in this case cyber physical production systems, and we developed some design strategies for these CPPS. Instead of having fixed, unchangeable, reconfigurable component connections, why don't we have mesh topology? And if there's something wrong with the actuators, then this actuator's job is taken over by some other actuators, or if there's something wrong with the sensors, then the sensor's functionality will be taken over by some other sensors. It doesn't make sense to build diagnostic systems per se. Instead of having a monitoring system, why don't you use sensors for any other purposes for monitoring? The idea is that, okay, instead of having a sensor for faulty behaviors, why don't you use the sensors for checking the arrival of components from the different station in this case? So here first there is a storage and one machining station, another machining station, so the components are moving around. And if you don't get any workpiece from the previous process, well, you don't have to monitor the previous process, previous station. You can easily detect the failure of the previous station by looking at the arrival of workpieces. In this way, you can implement fault diagnosis, well, at least fault detection mechanisms very cheaply. So these were the principles we developed, and well, I think this system actually demonstrated some interesting behaviors, like you can use for example, vibration sensors to detect the failure of a neighboring machining cell. If neighboring machining cell doesn't vibrate, then that means there's no working, and that means there's a failure. So maybe a component jumped, maybe some minor tool failure happened, but you can detect all of these problems very quickly. And I believe this is one way to cope with so-called short stoppage in manufacturing systems, and that's which is very difficult to deal with when the production speed is very, very fast. Okay, so I have talked about half an hour, or a little bit longer than half an hour, and I promised to stop after 40 minutes, so it's about the end of the story of my talk. I wanted to categorize my research using all of these research activities using these three categories, criteria. The first criteria is academic impact, idea-wise goodness. So you can talk about paper citations, you can talk about the follow-ons, you can talk about there's something wrong with the surprise in the achievement. You can also talk about application-wise criterion, which is maybe measured by patents. And then you can also talk about industrial impact. Did your idea get commercialization? Well, these are the three criteria you can talk about when you evaluate your own research. So, intelligent cat, well, I had reasonable academic impact. I believe I created reasonable, I had reasonable citations, so to speak. Industrial-wise, I'm not saying that I myself or my group generated some useful algorithms, but as a whole, the community came up with interesting ideas of intelligent CAD, so rule-based implementation of objects and rules to modify objects. All of these things made some sense. So I believe, as a whole, as a community, we created some industrial impact. But after all, was it a big success or not? I don't know. I'm not so sure. Maybe it wasn't that great. More particularly, if you look at metamodels, I had some academic impact. The paper is still referred, but there was no industrial impact. It wasn't a very good idea. So it is not a good idea. Qualitative physics, yes, we had some academic impact, but industry-wise, no, not really impact. FPS, academic-wise, it was a very big success. We had some academic applications, but not really industrial applications, so to speak, industrial impact. So in total, probably, well, it was a good research, but no industrial impact, so to speak. Design process simulation, well, our papers is still cited after 30 years. So academic impact was great, but not really industrial impact. Purely from academic point of view, it was good research. Self-maintenance machine, our papers were not really cited. It's disappointing, but the concept of self-maintenance was kind of game-changing, and we had industrial impact. So in that sense, it was good research. Silver machines, well, we had some small academic impact, but before we get some game-changing applications, before we could implement some industrial product, we gave up. So it was not even, we can't even say anything. Resilient CPPS, is it a good work? Well, the paper is getting cited, but we don't have any game-changing application or industrial impact, so it's too early to say anything. So these are my hopefully honest reflection of my research activity. Having said this, advice for younger generations, begin with your application. In other words, don't begin with your theory. You need to have very good applications. So to do so, you need to have very good industrial connections. Try to get problems not money, but get problems. And if you think you have a very good idea, stick to it. One day you really need to find applications, so but not solutions. So you need to have very good applications and good ideas, then that will lead to patents. And that's the starting point for great success. If you think you have generated only academically good ideas, try to write a paper that can survive for 25 years. In other words, you need to have paper which is general enough. Finally, good or not depends on technology. One of the reasons why we gave up with all these moving cellular machines was that at that time, Wi-Fi technology wasn't really mature. It was not just, it was not, well, it was just expensive. And we thought having only Wi-Fi is not good enough. You need to have GPS as well. Well, nowadays GPS plus Wi-Fi, that's everywhere. You can buy chips very easily, but at that time it wasn't that cheap. So we had some problems, and we gave up with continuing try to develop the concept further. But technology may change at any point, so you can have a different situations. Okay, do you have any questions? I'm happy to answer any.
Thank you very much for your talk. That was really, really fascinating. Maybe I'll kick us off with an observation in that looking at your talk, your questions are still extremely current. People are still working on functional modeling, on process simulation, on resilient machines. And the questions are still there, and the computer visualizations looked so dated that you had from the 1990s. But I think that the question stood the test of time is really interesting in your work. But what also struck me was that your success criteria were all external criteria. Has my research been accepted? Have I made a difference? Has industry taken it up? But I think the other aspect of a successful research career is work that maintains your own curiosity. And I was wondering whether you could comment on what kind of excited you through the years and what the sort of underlying questions were for you personally that you wanted to explore.
That was a very, well, your question was very, very stimulating, and there are people who say curiosity-based research is useless, but I think that's a little bit not really, well, it's discouraging, pretty much discouraging to hear that curiosity-based research is not that useful. However, if your research is done good, then whether it is application-based or curiosity-driven, if it is really good, then people get interested in your research. So that simply means, can you interest other people? It's not just about can you make other people, evaluate yourself or evaluate your own value, but is it possible for you to interest other people, simply draw interest? And I think that's one of the criteria that I didn't talk about. And yeah, I don't know.
Because I think the other aspect to what you're raising is that if you have curiosity-driven research, you see the implications of the things you're curious about in an application context. And that is often what gets research with a lot of impact, because you can put it into that bigger picture and then pursue it through that. Because I mean, something like functional modeling is an intellectually interesting question as well as a practical problem, and you can tackle it from both directions, and you need to have the curiosity from both directions in order to do it well, I think.
Yeah, I'm not so sure if function modeling was a good example in that case, but
well, it is for me. I find it intellectually curious.
Yeah. For you, yes. For people like Fermat, but when you talk to people in industry, for most of them, function modeling is nothing. When you talk to academia, who have to teach functions, who have to teach machine design, who have to teach architectural design, function modeling is nothing. It's only good for people who are interested in developing theories. It is very fascinating, but the value itself is not in the value itself is in the developing intellectual new field. That's the value for you, and that's exactly what curiosity is meant to be. And yeah.
So I was just wondering which of the research you did was interesting you most intellectually.
Yeah, but let me be honest. Outside our community, function modeling isn't that popular, and people use very carelessly the word functions, in my view.
Yeah, that's true.
And there's no distinction between functions and behaviors, for example. And when you ask some students, for example, to draw the function of something, then they very often come up with behaviors. Yeah, so it's not well understood, and still it's interesting that some people like us are very much fascinated the word function and function modeling, and yeah, how can we can we get interest from people outside? I don't know, to be honest.
Nor do I. I've also had a long-term go at it. But should we open this up to wider questions before we have a very specialized discussion on function? So does anybody have a question here? So just open your mic and say something. Martin, do you want to come in on your functional modeling question? Turn your camera on and turn your mic on if you want to say something.
Okay. I was wondering about functional modeling, whether the influence of functional modeling is more subtle than the ones that we've discussed so far, in that if people have some exposure to functional modeling in one of its various forms, it's going to have an influence on how they practice engineering, how they think about how to design or how designs work, or whether in practice this turns out to be fairly irrelevant, and the functional modeling, if people are told to go and do it, is froth on top of what they're really doing as engineers.
I think the biggest contributions of the notion function can make is the fact that it actually tells you the difference between what and how. So what is function? The how is how you achieve it, mechanism, for example. And if you understand the distinction between these two precisely, you are not going to make any more confusions. You're not going to mix up between what and how. So when you design something and you would like to invent a new mechanism, but still try to achieve something similar in terms of function, then look at the mechanisms only, physics only. And sometimes people mess up with the function and the behavior or physics behind it. So what's going to happen is that they try to introduce new functions when you are designing a new mechanism, and that will increase the complexity of design. And you end up with totally, wrong designs sometimes. So it is very important to have distinction between functions and the behavior and other stuff. And that's the biggest contributions that function modeling can make, I think, in terms of practical engineering activities. So you can teach students, you can lift something, but to lift something, there are so many ways to do it. And if you use the term lift, then you may forget that lifting is actually the same as pulling up.
Okay, thank you.
Yeah.
Do we have any other questions? So please open your mic, turn on your camera, ask your question.
Hi, it's Simon here. Oh, so I think Chris is going to ask a question. Chris, do you want to go first?
No, go ahead, Simon.
Sorry, it was more, first of all, I found your table really interesting, so thank you. Because I assess, like Claudia, based on whether I enjoy doing the research or not. And it made me reflect, yes, I should think about it differently. But my question, where I am, so I find myself between the fundamental, and yes, you could say maybe the purpose is only theory, and the application, and I recognize the importance of both, and find but one thing that I struggle with, and I just wonder this is for younger early career researchers, is how do you maintain the thread? How important, it's quite difficult to sort of say what a design professor does, especially if it's chasing the application.
Sorry, no, there was a connection problem. So can you rephrase your question again, please?
Yes, sorry. So it's saying that because yeah, it's my London internet is not that brilliant. The challenge between the balance between application and industry focus versus the fundamental theory. When you're focusing on something functional modeling, or whether it's creativity theory, whatever it is, you can have a clear thread of your research. When it's application driven, we're moving constantly. And what would be your reflection or advice on particularly early career researchers around it?
That's a very tough question, to be honest. I also struggled a lot in chasing after money. You end up with the feeling that you are not doing anything serious in terms of research. And well, what should I say that? One of the things that I noticed, maybe not from my own research, but from other people who are successful, sometimes people are really good at in transforming applications into practical applications into theoretical challenge. And I think you need some training there. But for example, if you like to solve some, design issues, real engineering design issues, but still you can convert it into functional modeling question, for example. And that type of thinking always help you. I don't know if it helps, but hopefully helps you to write academically super papers. That's sometimes that's what people must be trained for that, I think. Yeah. I don't know if it's an answer to your question, but you have to be good at transforming practical questions into theoretical challenge. Yeah.
Thank you.
Chris, you're muted in case you're trying to speak. Okay.
Thanks very much. Thanks very much for that, Tommy. That's a very interesting presentation. I wonder whether you had any comments on how the research environment, the research landscape has changed over the years. I mean, you seem to have started in a relatively small, quite dispersed community and moved into much larger, much more established communities. What's it been like working as a researcher in those different circumstances?
I don't know, to be honest. You have to be able to accommodate to different environments. That's number one. Number two, certain environment has very much fixed protocols. You have to, do in Rome, do as Romans do. So basically, you have to change your behaviors fitting to your environment. And so when I started, it was pretty much design researcher, but then I started to work with AI guys or CAD guys, and they had different protocols, they have different focuses, different research questions, which I never had. And so you have to change. And if I go to ASME, they have their own protocols, and I was never successful in getting ASME as kind of thinking. My papers were constantly rejected by ASMEs. When I became an ASME fellow, I was one of the, probably I had only 1 or 2 ASME papers, and still they made me a fellow. So writing a paper doesn't really matter for them. But yeah, I mean, things like this. And yes, yeah, different groups have different ideas, different, yeah. I don't know.
Yeah, I think that's exactly right. Very important. I mean, geographically, temporally, different communities. Thank you.
Yeah.
Do we have another question? That's probably our last official question, then we'll close the seminar, but you can stay online and we can ask a few more questions. Ross, do you want to do some announcement about the next seminar, and then
there's someone who is asking questions.
Yeah.
Yes, I would ask the following question. We have in Ilmenau, the next seminar comes from Ilmenau, and we have a cave, and we are modeling cars and other machines, and our problem is different physical properties to simulate in time with a very good short time of the answer. Do you have any comments and any orientation for us?
I'm not sure if I understood your question fully, but are you talking about multiphysics kind of simulations, or?
Yes. Mm-hmm.
Well, I don't know, but yeah, you have to have a very good simulation software, and there are a couple of them, and one of yeah, some softwares are more dedicated than general purpose software like MATLAB. So you really have to invest in those dedicated simulation, multiphysics simulation software.
Okay.
Yeah, that's all I can say as long as I hear from my colleagues.
Yes.
Yeah.
Okay. Thank you.
Yeah.
Do we have any other questions? I think, as I suggest, in that case, we'll simply officially close the seminar, and you can feel free to leave and feel you've stayed to the end of the seminar. But if we want to continue an informal chat, then we can, of course, do that. So do we have any informal questions in that case?
Okay, thank you very much in that case. And yeah, I enjoyed the seminar. I saw a lot of my former students, so to speak, were listening to. And thank you very much. By the way, I enjoyed your talk, Chris. Yeah.